this objective is not only for today's class, for the series of classes that we are going to have. We'll be talking about what is the need for signal conditioning, of course, amplifier to start off with. Then we go to op-amp, operational amplifier. Okay. You people have learned operational amplifier earlier as part of some basic electrical course, electronics course. So op-amp will learn. And how to use op-amp for summing, for averaging, or integration, differentiation, how to use that circuit we will learn. Okay, that's a major portion in the course of time. We'll talk about the filters. And filters per se is big topic. People study signal processing as a separate subject in electronics. A lot of advanced stuff are there. But what we will be doing is what is low pass filter, what is high pass filter, what is band pass filter, we know as a definition. And we just learn how to design an RC filter. RC means resistance capacitance filter. That's very simple stuff. Just to have an idea about filter design. But there are quite complicated filter designs available. We will not touch all. Just an introduction to filters. And we'll also touch upon the voltage divider, charge amplifier, and scaling device. Of course, we should be already seen. So, since the order is changed here, we are already seen, so that will scale. So that's the idea. We have plenty of sensors in the world. Okay, either you might have already come across or you will be coming across plenty of sensors. I have listed few of them. Take an image from Google and list it. Not my image, not made of it's already there in the Google list. Plenty of sensors for a variety of measurements. Okay, what is the problem? Problem is, before Cat 1 we just learned the working principle of thermography. Working principle of thermography. What did we do? What did we learn there? If there is a dissimilar metal and made two junctions, that means I am joining one end and the other end. One end I am keeping it at a higher temperature than the other end. Then the dissimilar metal and difference in temperature results in thermo EMF, resulting in thermoelectric current. And this current or this thermo EMF is proportional to the temperature difference. That's the theory that we have learned. Okay. So now we know I went to market, bought one thermocouple, connected it, and connected one voltmeter or ammeter or nullmeter. In the curiosity to know what is the voltage that is going to come. Okay. And also I started heating one end of the thermocouple. My general expectation is the moment I start heating, I want the needle to move and then show 1 volt, 2 volts, 3 volts, or 1 amps, 2 amps, 3 amps, or 0.1 amps, 0.2 amps, something like that. Some tangible reading we are expecting. But if you connect a thermocouple directly to a device, you will see for most of the temperature that you can create, maybe you take a candle and heat at one end of it, you will see the needle of either the voltmeter or ammeter. Now we are connected across, in the as an ammeter board, the series. So it's an ammeter. The current that is going through the where are you? The current that is flowing through the ammeter is very less. Earlier, before connecting, it was in zero. Now it is close to zero. That's all. It's not exactly zero, but close to zero. It has not even made the first division. So I am not able to read anything. There is no tangible current, the thermo EMF, the thermoelectricity that's coming out of the thermocouple. That's a serious problem. I cannot do anything with that. If some number, 1 volt, 1 amps, 0.1 amps, something is coming, which I can measure it using a galvanometer or ammeter or voltmeter, multimeter, then I can calibrate that. 0.1 amps means corresponds to 5 degrees Celsius. Every 0.1 increment is 5 degrees Celsius. Something I can make a table or a calibration equation, and then finally I can end up in getting the temperature. If I am not able to read anything from the meter, then what will I do? That's a serious problem. That's a serious problem in the brain. Because the signal that is coming out of thermocouple due to temperature. I wanted to measure the temperature. Because of the temperature is very, very small. I am not able to even read. I cannot do anything with that. But the theory says proportional to temperature, the thermoelectricity is produced. Either the current or EMF, both are proportional to temperature. I am sure something is coming proportional to that, but my device is not sensitive enough to measure it. Either I can go for very sensitive galvanometer or sensitive ammeter or a sensitive voltmeter connected, try to measure that and calibrate. But that results in huge amount of cost, because anything in industrial atmosphere you wanted to sell for a research purpose or for argument's sake, if you want, you can buy one very costly ammeter which will measure 0.001 amps, that means 1 milliamps, or even 0.1 milliamps, 0.00001 amps. These also devices are there, but only thing, the cost is very high for such precision meters. Okay, very accurate meters, the cost is very high. People will not be able to afford from industry point of view. Okay. Thermocouple based temperature measurement devices are available for 300 rupees, 400 rupees today. Okay, and you say multimeter alone, forget about the thermocouple, multimeter alone, you say 3,500 to 5,000 rupees. Then only I can measure the thermocouple, and then thermocouple for range of temperature it will be different. I know it starts from 1,500 rupees to 5,000, 8,000, 10,000, depending upon the material combination that goes inside the thermocouple. And manufacturers and other tags, everything from 1,500 to 10,000 rupees, the thermocouple sensor cost will go. You say for measuring the current or voltage alone, I am spending 4,000, 5,000 rupees worth of meter or multimeter. People are not ready to buy. People are not ready to buy. So the only way is there is signal coming in the wire, but I am not able to perceive it easily. I am not able to sense it easily. That's a serious problem. The magnitude level of the signal is very low. So if I have some device which will amplify the magnitude of the signal, then probably I will be able to easily measure. Okay? I want a device which will amplify the signal. That's why the amplifier comes into the picture. Okay? The amplification is needed for this signal that comes out of thermocouple. Not only thermocouple, thermocouple I have taken as an example. Any device which gives very, very low signal, low voltage, you need amplification device. Right. Now what I did, I assume I built one amplifier connected to thermocouple signal, and now the signal is amplified and reasonably good voltage is coming. Now I am happy and I have connected to a CRO, because CRO you can use it for measurement also. Two things that you can do: one, measurement; other one is visualization. CRO gives a graphical representation of your signal. Okay, you can also measure. You can also visualize what is the shape of the signal. In multimeter, you can only measure the RMS value, isn't it? So if voltage is given, you connect the voltage, it will show 1.5 volt, 1.7 volt, something. It will not show you, hey, you should not sleep. My camera phone will fall down. I don't have enough money now to buy another phone. Be very careful. The way you hold the camera, there's all possibility that you will leave it. Okay, you have to be awake and be careful. What is your phone?
Sir.
Is Redmi something of similar model or low cost? Better version. Then you can hold it. No problem. So I have connected the signal to a CRO. Now I am getting some waveform. Noise is coming.
Yes.
Some noise is coming. Not only from outside, in signal also some noise is coming. Okay. So when I see this, I expect something signal like this, a straight line like this. Because let's say now the thermocouple is experiencing some 45 degrees Celsius. Proportional to that 45 degrees Celsius, I want some 0.12 millivolts. It is voltage that I am measuring. or zero point 0.1 milliamps, some current, very low current. But it is a fixed value. I want a line. I am expecting a line in CRO. It's a DC because temperature is not going to vary in a fraction of a second. So temperature, even if it is increasing, it will slowly increase. Or if you allow it to cool, it will slowly cool down. Only if you quench it in oil or water something, the sudden drop in temperature may happen sometimes. But sudden increase is very difficult. Normally it takes time to get heated up. The rate of heating may be high, but it's not a dynamic signal. It's more or like a quasi-static signal. Temperature is a quasi-static signal. Slowly it will increase or decrease. So I am expecting either a perfect straight horizontal line or with a small slope of increasing or small slope of decreasing. But I am expecting a line. But what is it I am getting here? A lot of noise here. Lot of noise. And also in between there are bigger peaks. Even this I can eliminate, but there are some bigger spikes that's coming. Again, these are all noise that's picked up from the ambience. Various types of noise that we have already discussed during the sources of error. Okay, for thermocouple measurement, suppose if you do a thermocouple measurement here, you see there is a high power line that's going. That Tamil Nadu electricity board gives 50 hertz, 240 volt, 5 amps current to this kind of industries. We are in a part of industrial category. As far as they are concerned, we are industry. So that 50 hertz signal will get superimposed to this DC signal. You will see probably a sine wave of 50 hertz along with the 0.1 volt, 0.2 volt, whatever the signal that we have. So you will get a superimposed a wavy signal instead of a constant signal. Today you have a lot of radio stations, we use a lot of phones, we also use Wi-Fi inside our campus. All these are potential factors which will affect my measurement. Everything can get into my wire if proper insulation is not given and get into my wire and come and act as a noise here. So that will vary. How I will protect it? To a greater extent, we can provide some insulation, but again it is a cost factor. Insulation is you use very costly wire. Maybe most of the noise you can avoid getting into the wire itself. That's coaxial cables are there. But again, due to cost factor, we use cables, normally single strand or multi-strand cable, simply a wire we will use with the plastic protective coating, that's all. Thinking that we can manage most of the noises in the signal processing. So due to cost factor, we use wires which commercially we will be able to afford. Both mechanical strength and current carrying capacity alone we will take care. Other protections in certain applications, precise applications, we do take special care and use special cables. But most of the applications it is not affordable. For a small temperature measurement, I cannot use a very costly wire. I'll give you an example. I have a accelerometer, and the cable alone is a 3-meter cable, 6,000 rupees. I bought about 4 years back. Now it must be around 8,000 rupees. If you doubt me, you simply go to ni.com, that's nationalinstruments.com. Accelerometer, coaxial cable, connecting accelerometer to data acquisition. One cable is there, connected, DHC connected. The cost is not because of DHC connector, the cable also. So 3-meter cable is costing about 6,000 rupees 3 years back, 3-4 years back. So we cannot afford that kind of cable for all the sensors that we have. So we buy some normal wire, and wire is picking up noise, then coming inside. So I get something here. When I get noisy signals, I may not be able to get the actual temperature. Because normally what multimeter kind of devices do is they take the RMS value of whatever is the voltage that's coming here. Put the link down. This RMS value. So I am expecting a constant DC signal. Even if there is a small white noise, while taking RMS, that plus and minus component may go at least, I'll get more or less close to the actual value. Still the error will be there, but the error will be less. But you see the peaks are there. Or as I told you, 50 Hz signals are there. The RMS value is boosted than the DC value that we are interested in. but that is not the temperature we want because the device is already calibrated for pure DC signal. Now if AC noise is coming, you will get a wrong reading than what you expect. You expect some reading, but it will show some other reading. You will not know whether it is wrong reading or right reading when you have only one thermometer and you are simply measuring a component's temperature. It will show some temperature. That results will be misleading. So we would like to have a filter to remove all these kinds of noise so that my signal is purely a DC signal in this case. In certain cases, what the signal what I am measuring may be also a dynamic signal. Even there, I would like to remove the noise factor. Okay, we'll talk more on filtering as we enter into that topic, but filter is needed. So far, we have discussed the need for an amplifier, the need for filter. This next is this, the development of computers and also microprocessors reduced the cost of the computing. Earlier, one computer, if I have to have, it's about in those days about 45,000 rupees. I am talking about when I was doing BTech like you. Today also it is 45,000 rupees. You will get a computer. It may cost 45,000, but the amount of processing capacity and memory that goes into that is very high in today's market price. Okay, 45,000 rupees. When I was like you, BTech student, about 20 years back, the same 45,000 if I give, I may get a 346 system or 446 system. Not even Intel Pentium. There are lower versions of processing chip capacity with 512 MB RAM, maybe lesser than that, and 1 GB, 2 GB hard disk configuration device you will get for such a costly price that we pay. Of course, today if you pay that, you will get i5, i9, alright, 45,000 rupees you will get a very fantastic computing device. The microprocessors cost have come down. Arduino, 1,200 rupees. Of course, it's available from 600 rupees in certain online markets. Okay. Any microcontroller or with data acquisition capacity, so you get it at 1,000 rupees. 1,000 bucks you give, you will get data acquisition card with computing facility. Okay. But in those days it was a bit difficult. Not only we had 80, 85. You have to program using mnemonic codes and data acquisition extra module you have to add. A lot of drawbacks were there. Today you have plenty of computational resources and all your sensors for company automation, you would like to connect it to that particular digital device. The problem is, we understand the world gives only analog signals. Very rarely it gives a digital signal. Very rarely it gives digital signal. Most of the signals in the real world are analog in nature. Computer understands only digital signals. There are analog computers, but they are not in wide use. There are analog computers as well, but they are not in wide use. Whatever the laptop, cell phone, the Arduino or other kind of microcontrollers that we have, they are all digital in nature. Okay. So they understand only digital language, and the world speaks analog language. Then comes there should be a converter who translates the analog to digital and the reverse, the digital to analog. Okay, because we not only wanted to know the real world items to the computer also wants to speak back to the world for control applications. For example, I want to measure temperature, I want to measure pressure. Based on that, I want to control the flow rate. There is an industrial application. For measuring temperature and pressure, analog to digital converter is needed. So those analog signals are converted to digital signal, computer understands. After understanding, based on those numerical values, I want to adjust the flow rate of certain item. Then this has to give some signal. It will give the command in digital. That digital to analog conversion is also needed. Then that analog signal goes and does the control operation to vary the flow. So analog to digital converters, digital to analog converters, both are needed, so that we will be able to take advantage of the computing development in the hardware in the computing industry. So to sum up, we have plenty of devices that gives us amplification, filtering, analog to digital conversion, digital to analog conversion, scaling devices like typically they're all transformers, step-up transformers, step-down transformers. They are basically scaling devices. They don't amplify; they only scale. At the cost of current, voltage is increased, or at the cost of voltage, current can be increased. So they are all basically called scaling devices, switch bridge, voltage dividers, lot of stuff. Okay. What is our scope? What is that we will be learning, sir? That's a big ocean. We will not be able to learn all of them. But our subject is restricted to, or we will be restricting ourselves to mostly these items. An amplifier. We start off with what is it? NPN transistor-based amplifier today mostly, and quickly I'll try to complete. I think we have taken a lot of time on introduction. Of course, that is needed, so we need to do it. And then tomorrow, probably we start off with our operational amplifiers. Then we talk about summing amplifier. What are all the mathematical operations that we can do with operational amplifiers? We will learn as part of amplifiers, and of course the integrators and differentiators. So these two and first one go as a match. And then, of course, filters, as I told you, basics of filters we will learn. We learn the analog to digital converters in detail. Analog to digital and digital to analog converters in detail. So we should be able to do, because that we practically do. As a mechanical engineer, you go tomorrow. Any automation that you think, let it be CNC machine, let it be robotics, any automation in the industry that is being done, analog to digital converter is the very first thing that you should know very well about. Then only you can understand how the system works. Bridge circuit we have already learned. Rectifiers, and you might have learned, but we will refresh it and learn it here. And then voltage divider, that is just 5 minutes to start. These are all the items that you should know in order to follow this subject well. What is this? We have some signal coming from sensor. We should be able to amplify it, scale it, do certain things, and calibrate it and show the actual value. If 45 degrees Celsius means 45 I wanted to show. These are all the items that you should. So I will be restricting my discussion to only these topics. Plenty of other topics are there, but we will not be able to do. We will be able to do justice only to these topics because we have limited amount of time. Okay. Amplifier. Amplifier is a device which magnifies the amplitude of the signal or magnitude of the signal with faithful reproduction with the help of external power source. If you want to call a device as an amplifier, these three conditions have to be satisfied. What are they? The device should increase the magnitude of the signal. It's magnitude, right? Amplitude of the signal. Increase the magnitude of the signal. Number one. Number two, it should faithfully reproduce the input signal. I'll talk about what is faithful reproduction. Number three, it should use external power source for its amplification. If these three items one device is using, let it be any device. I don't know how other people are going to call. At least we will call that device as an amplifier. We will call that device as an amplifier. Okay. So amplifier is a device used to increase or magnify the power level of the signal. Increase the amplitude of the signal. With other conditions, it has to increase the power level of the signal. So the correct terminal is this power level of the signal. With faithful reproduction, using external power source. Using external power source. What is meant by faithful reproduction? Sorry?
The shape of the signal
should not be changed. I give a perfect sine wave of 50 Hz to a device. After amplification, I get a bigger sine wave. It is not sufficient I get bigger sine wave. Also, the same exact 50 Hz signal should come. There is no change in phase angle. There is no change in the shape. If I give a sine wave, it should be sine wave. If I give sine wave, cos wave should not come. or a distorted sine wave should not come. So if I give sine wave, the sine wave should come of same frequency, but amplitude should increase. Increase the power level. So that's what we mean by faithful reproduction. And the external power source it has to use, you will understand why. And if the device increases the power level of the signal, it will. Okay, these three conditions you can satisfy. You call the device as what? Amplifier. We'll take a case study. You have a step-up transformer. You have step-up. You heard of step-up transformer? What is the function of step-up transformer? You give 100 volt to the primary, and you step up to 240 volts, something like that, isn't it? So a lower voltage is increased to a higher voltage. So you give 50 hertz 100 volt input to a step-up transformer. You get 50 hertz 240 volts output. It's possible, quite possible. I have a transformer like that. Can we call that transformer as an amplifier? Because it amplifies 100 volt to 240 volt. Can we call that device as an amplifier? No? Yes or no?
No, sir.
Why? Huh?
It reduces the current.
So what?
Voltage alone increases, sir. The current is reducing. That's,
Voltage alone increases, current is decreasing. So what?
it's not actually.
Actually?
It's not actually reproducing the same value.
It is actually reproducing.
So it changes its shapes.
Energy? Yeah, power level. It's not energy. Its power level is constant. Okay. The power level is constant. You are right. There is nothing wrong. Your answer is also right. So voltage is getting increased at the cost of current. So what is power? Power is given by voltage into current into power factor. Okay. So normally your transformer power factor will be around 0.9, not 1 actually. There will be small loss in the power. So totally, if you give 5 watts power as input, 4.9, 4.8 watt power only you will get at the secondary. Okay. Whether you get increased voltage or decreased current or vice versa, the power level will be less in transformer. So power level, if we assume power factor equal to 1, the ideal transformer, even then the power level will remain same. The 100 volt, maybe 10 amps current is changed to 240 volt, 5 volt, what is it? 100 into 5, 500, right? Okay. This will become 250 volt, 5 amps current. Is the equation matches? No. Voltage into current should be equal to same. Okay, so the current is reduced. 2 amps current, right? 250 volt, 2 amps current you will get. So current is reduced, voltage is amplified, but power level remains same. Power level remains same. Theoretically speaking, power level will remain same from input to output in transformer. So we cannot call this device as an amplifier. So any device, see, because your CAT 2 is open book test. Questions will be like this only. They will not ask define amplifier. What is amplifier? They will give one device, ask whether this device can be called as an amplifier. Answer will be simple. Marks will be 10 marks, 5 marks, something like that. Only if you know you can get it. So understand how to apply this and then answer logically. I think this you will be able to easily understand. Till what time this class goes? 8? 9:45. Okay. I don't know whether they will follow. Okay, let me try. This is a valve, let's say a pneumatic valve operated by pressure. Here there is a small pressure that I can give. There is a bellows. Bellows means a balloon structure. I already explained what is bellows. So here you apply pressure to bellows. Bellows will expand and push this knob 1 towards left. The rod, this lever, the lever is hinged here. That means the rod can move like this. In the plane of the board, it can move like this. So the knob pushes the lever towards left. So knob 2 is also pushed towards left to a greater extent. To a greater extent. This pushes a little, but that results in large angular displacement here. That pushes the pulls the valve spool to a greater extent. That results in opening of this valve. Here I have a high pressure source through which the high pressure air is coming inside. Initially it is completely closed. Now the valve opens. Because of opening, the output pressure is going outside. This is the working of this structure. How does this device is related to an amplifier? You see, now I give a small pressure, there is a small expansion, there is a small leftward movement, there is a small opening. Proportional to that, there is a air coming out with some pressure. That is proportional to the amount of pressure that I give. Suppose if I give 1.5 bar, there I can get some 5 bar. 1.5 bar, let's say 3 bar. Okay. I increase the pressure to 2 bar, here I will get 4 bar. Because more opening. Proportionally, if I get 3 bar here, I will get 3 into 6 bars here. So there will be a constant factor, which is amplification factor, and as I increase the signal pressure, I keep on getting higher and higher pressure from there. Okay, so I'll get the. There is a limit beyond which I cannot go. Okay, that's called saturation point. So only 10 bar pressure is coming here. That means I can go up to only 10 bar. Even if amplification factor tells I have to supply 11 bar, I will not be able to supply. That's the restriction. So it is a saturation point. So proportional to the signal pressure, I am getting the pressure there. Okay. You put everything inside a box. You put everything inside the box. All of them. I'm going to call this as an input. I'm going to call this as an output. Okay. Rest everything is inside the box. I am giving a small 1.5 bar pressure. I am getting 3 bar pressure. I am getting 3 bar pressure. You apply your the 3 conditions of 3 conditions to call a device, or qualify conditions to be qualified to call a device as an amplifier. Okay, there should be increase in power level of the signal. Okay, power level for hydraulic system like that is P into Q. P into Q is power. 2 pi 80 by 60 is mechanical power. P into Q is hydraulic power. Vi cos phi is electric power. There are only 3 powers. There is no other equation. Just these 3, if you know, mechatronics is over. Okay. So hydraulic power is P into Q. P pressure times discharge. Here I am giving some pressure, some discharge. I multiply pressure and discharge. Here I multiply pressure and discharge. Is it increased now, or will it be same or decreased? From the diagram itself you can tell small pipe, small pressure I am getting. So the power level will be very small. Here there is a big power source that is attached, a big pipe through which more high pressure air is coming out. Pressure is also high, discharge is also high. So I will have big power. Power level is increased. It uses external power source. See, there is an external pressure source that it is using, external power source it is using. 2 conditions satisfied. It should reproduce faithfully. That means if I vary the pressure here sinusoidally, here also the pressure variation should be sinusoidal. Increase in pressure, decrease in pressure, sinusoidal. If I increase like a sawtooth, increase, suddenly drop. Keep on increasing, suddenly drop. That is sawtooth waveform. or triangular waveform, whatever. You suddenly keep on increasing, keep on decreasing is triangular waveform. Keep on increasing, suddenly drop is sawtooth waveform. All these kind of signals are all test signals which we can visualize. That way you vary, same shape I am getting output. So there is a faithful reproduction of input signal with output signal. It amplifies magnitude or no sorry power level of the signal. It uses the external power supply. It has faithful reproduction. Can I call this device as an amplifier? Yes, we can call this device as an amplifier. This is pneumatic amplifier. It's a pneumatic amplifier. Is there any doubt in working of this? Is there any doubt in working of this? Because if you don't understand this, I'm going to use this as an analogy to explain the NPN transistor and then how to use that NPN transistor as an amplifier. We are going to move towards electronics. If mechanical itself is not clear, then of course electronics will become a nightmare. Any questions? Anything already planned? Okay. We'll stop here. Okay, because I will not be able to complete that. That needs about at least some 30-40 minutes of continuous discussion. So probably next class we will take up and then discuss. What I request you